Sound travels at different speeds through different materials. That's why when you tap the top of a glass, you can clearly hear the difference between the sound made by tapping the glass with a wooden hammer and the sound made by tapping it with a metal hammer. But how does sound travel? And what determines its speed through different materials? That's what we'll explore in this episode of Physics Puzzles. When you tap a glass, the hammer gives the glass a little nudge, which disturbs the molecules in the glass, pushing them out of their usual positions. These molecules collide with ones next to them, giving them similar disturbances that they in turn pass on to their neighbors, and so on. This domino-like propagation of molecular disturbances is what carries the disturbance that we perceive as sound through the material. The greater the number of collisions that carry the sound disturbance in a given amount of time, the higher the sound's frequency, and the higher the pitch we hear. In a solid like the glass in our example, the molecules are close together, so the disturbance can be passed from one molecule to the next very quickly. In other words, sound travels fast through solids. However, if we instead disturb a fluid's molecules by tapping the container holding it, the molecules have much more freedom of movement and the disturbance gets passed along much more slowly. So sound travels more slowly through liquids than through solids. If the container holding the fluid is flexible, like a balloon, you can see the disturbance traveling through the fluid like a wave. But if you have a gas in a rigid container, then you can still hear the sound, but it takes a long time for it to propagate through the gas. This is because even though the gas molecules are in constant random motion, that doesn't make them more tightly packed. So there are many opportunities for the molecules to collide with each other and pass the disturbance along. When the molecules do collide, though, they transfer energy to each other quite efficiently. So once the disturbance is propagated through the gas, say by vibrating the container, the sound will propagate quickly through the gas. So in general, the closer the molecules in a material are to each other, the faster sound travels through that material. But why does the sound of a glass being struck by a wooden hammer sound different from that of a glass being struck by a metal hammer? That's because not only does the material that the hammer is made from affect the speed of the sound, but it also affects how well the sound is transmitted into the glass. Some materials are better at transmitting vibrations than others. For example, if you hold a metal rod with your hand, you and be able to feel vibrations traveling through it, unless you press your fingers hard against the rod. By contrast, if you try to hold a wooden dowel with your hand, you'll feel vibrations much more easily. We call a material that transmits vibrations well a good conductor, while a material that doesn't transmit vibrations well is called a good insulator. Good conductors generally consist of molecules that are both close to each other and bound to each other tightly. For example, metals are typically both dense and have strong bonds between their atoms. They're therefore good conductors of sound, which is why a metal hammer strikes a clear note when hitting a glass. On the other hand, good insulators often consist of molecules that are either far apart or bound to each other loosely. Rubber is an excellent example. You can strike it with a hammer and hardly notice it, but is also a good insulator, although that's partly because it's not particularly dense. A related concept is that of acoustic impedance. This describes how difficult it is for sound to pass from one material to another. The larger the acoustic impedance mismatch, the more the sound waves will be reflected back into the material they came from, rather than passing into the other material. Let's return to our glass again. Glass is a good conductor of sound. However, air is not. So when sound passes from the glass into the air, most of it gets reflected back into the glass. It's this sound that we hear as the hammer hitting the glass. By placing something like a piece of cloth over the top of the glass, you can actually dampen the sound considerably. This is because the cloth acts as an insulator, reducing the amount of sound that gets transmitted into the air. Incidentally, this damping effect is why musical instruments often have hollow resonating chambers with necks that lead to the outside. By changing the length of the neck, the instrument can change the amount of sound that escapes through the neck and is lost to the air. This changes the acoustic impedance of the instrument, and thus the sound it makes. Another factor that affects the speed of sound is temperature. Higher temperatures generally mean that sound travels faster through a material. Let's think about why this should be the case. When you increase the temperature of a solid, you increase the kinetic energy of its molecules. This means they vibrate around their equilibrium positions more vigorously. More vigorous vibrations should lead to the molecules colliding more frequently, which should allow the disturbance of sound to pass through the material more quickly. And indeed, experiments confirm that sound travels through solids faster at higher temperatures. For liquids, the situation is a bit more complicated, but it turns out that the increased kinetic energy of the molecules allows them to overcome some of the forces holding them together, making it easier for them to pass on the sound disturbance. So sound also tends to travel faster through liquids at higher temperatures. In gases, the situation is similar. At higher temperatures, the molecules move faster and collide more frequently. Additionally, the increased temperature makes the molecules move farther apart. As we've seen, the farther apart the molecules are, the faster the sound can pass through the gas. Both effects contribute to the fact that sound travels faster through gases at higher temperatures. And we've now answered all the questions you've sent in. Thanks for watching. If you want to send us some questions of your own, go ahead and do you know what? Just like sound, light also travels at different speeds through different media. You can find out more about this in our video Light Speed.